All right, so really quickly, I'm not going to do an entire problem, but we had that handout last time. Anybody not get that handout last time about the probability distributions? I think it was time before the quiz. Yeah. Last time we did new stuff, I guess. Okay. So if you weren't here, you can watch the video. You can come see me. But we developed this way of doing stuff. This is part of a formula, right? So if I add up, oops, got it. If I add these up, I get the mean. If I add these up, I get a part of the variance formula. My God, and I wish to God everybody could remember, we actually kind of created these formulas. And it's so easy to forget that and then to start looking, here's more math shit, plug shit. No, we created these formulas. We made them do what we wanted them to do. And now we can use them. That's how math is. Not just me saying, use this, plug it here. You know, we actually did this together. So whatever number you get when you add these up goes here, and you subtract the mean squared. Cool. Of course, this is the variance. So then, of course, I take a to get the square root to get the standard deviation. Square root of all that. So, you guys, that feels very familiar. It's a little bit easier formula, actually, than what we had back in chapter 2. Cool. I like it. I like it. So that's section 4.1 and 4.2. So we're going to get into section 4.3 now. So somebody remind me before we get into there. When I have a probability situation where it's and, what do I do?
Multiply.
Well, when I have a probability situation where it's or, add. I love it. I love it. So we went through a lot of stuff. And that's one of the most important things to get out of everything we went through in that chapter, is those two things you just said. Okay, so now watch this. What we're going to get into now, remember how I had to be very specific about you pick a Twix and then a Butterfinger, right? Because if I said the probability of getting exactly one Twix, well, I can get a Twix and a Butterfinger, and then or a Twix and a Snickers, and so if I said exactly one Twix, for example, and I picked three candies. How could I get exactly one Twix? Well, it could be Twix, Butterfinger, Butterfinger. It could be Twix, Butterfinger, Snickers. It could be Twix, Snickers, Snickers. It could be Twix, what do I leave out? Snickers, you start to get into the point where now I've got to calculate all of these. So what I want to do, number one, that explains why I had to be very specific, so that you know exactly which one to calculate. And now we're going to let it be exactly one Twix, but we're going to develop an easier way to do things. Especially if there's only, that specific one wouldn't work, but if there's only two options. So this is called a binomial probability distribution. Binomial meaning two options. Two things could happen. Binomial prob dist. So to make this a little bit easier to work with, let's talk about left-handed versus not left-handed. Right? Because I can't just say left-handed, right-handed, because some people are ambidextrous. I love it. I want to see who knew the word. Right? One person in their senior quote was, "I'd give my left arm to be ambidextrous." Well, you're such a funny person. So let's say that we know that the probability of a left-handed person and again, the last time I checked, it was still 11%. roughly 11% of the population of the states is left-handed. Remind me again, who in here is left-handed so I can... Okay. So instead of writing probability of left, because the only other possibility is that you're not left. Is that cool? I could say right-handed, but just to make it more general, I'm going to say left-handed, not left-handed. Right? So probably not left-handed would be what?
Oh, sorry. 0.89.
Yeah, this would be 0.89. Is that cool? Of course, right? Because together they have to add it to be 100% or 1, because that's everything. I like it. What if you don't have any hands? Well, then you're not left-handed. Not to be funny, really, but somebody brought that up. Well, that's why I said this, to just cover everything else. I'm sure you guys are looking for people. There are people without hands. I'm sorry, it's true. So then you would be in this category. I've got a category. So let's do this. So these kind of problems are always going to have two possible outcomes. So would rolling a die do this kind of thing?
No.
You could make it so, couldn't you? So you're playing Yahtzee and you need 5s, and you're probably getting a 5 and the probability of not getting a 5. So basically you can make anything become this if it makes sense in the problem you're working. Are you guys understand? Probably this, probably not this. Evens odds, if it naturally breaks up into half and half, beautiful, right? Or into opposites, beautiful. Okay, so let's say I pick 5 people at random. All right, poor little blue dudes almost there. Pick 5 people at random, and I want the probability that exactly one of them is left-handed. Now, I'm picking a problem where it's easy to actually list everything that could happen. And then I'm going to show you, and then we're going to develop a formula. And then we're going to go, well, it could very easily become a problem where I do not want to make the list, because the list could be tens of thousands long. This list is going to be very short. I've got 5 people. Right? How many ways could there be one left-handed person? It could be the first person. Now, before I get too far, I was about to say something up here and I forgot. There's only ever going to be 2 options, so let's call the success one, the probability of success, the thing that we're looking for, let's call it P. And the probability of failure, the thing we're not looking for, we'll call it Q. So, us not left-handed people, we're not failures because we're bad people. We're just not what we're looking for. So, the success could be a bad thing. It could be a dead body somewhere. It could be a rabid squirrel. It could be, right? A rabbit squirrel is the cause of the dead body. I don't know. I wasn't there. So success just means it's what you're looking for. You could be looking for good things or bad things, depending on what your job is, right? Okay. So how many ways did you get exactly one left-handed person? So the first one could be left-handed.
Or what?
No. The first one is left-handed. And, okay, thank you. Somebody. And the next one's not, and the next one's not, and the next one's not, and the next one's not. Is that cool? So why does this make sense? In algebra, when I write letters together, that means I am doing what with them? Multiplying them. And of course I'm multiplying these because it's this and this and this and this. That's one situation. Or, what else could happen? Second dude could be or dudette. I don't know. Q, P, Q, Q, P. I think now you see the pattern here, right? This P is going to just float. That's right. Plus Q, Q, P, Q, Q. You guys with me?
Yeah.
So this one's an easier problem. I actually don't need the formula we're going to create for this problem because I can actually list all the things that could happen. And when I can do that in probability, I can just do it directly, no formulas. That's why it's a good one to create the formula, because I can't always do this. Plus Q, 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 P, Q, plus Q, 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 P. Okay. If you get the pattern, you shouldn't have to be able to see all that. but it's just the P floats, floating P, yes. Now, algebra would kind of laugh at the way I've written all this, right? And so should you, because you've all been through algebra. So how would I write this in a better way? P times Q times Q times Q times Q is P times Q to the fourth. Isn't this the same thing? Isn't this the same thing? Isn't it? And how many of them are there? So I'm going to have 5 PQ to the fourths, right? And let me do something we normally don't do just to really put it in your face. What's the exponent on the P? 1. So there's only one part of what I've written that didn't come from the question. Exactly one left-hander. And what was the left-handed person? We called them P, right? So how many P's are there? Oh, okay, I wanted one of them. So it means how many failures must I have had? 4 of them. And the only piece that didn't come from the problem is that tells me how long the list is, right? Now this list was deceptively easy and small, easy to make, and it was small. But maybe I can convince you in a second that it's not always going to be that way. So let's see, this will be, and now I can just plug this in the calculator, right? What was P again, the probability of left-handed? So that's 0.11. I want one of those. And I want 0.89 to the 4th power. So try to plug that in your calculator. If you need to borrow one, do so now. Okay. Oh, so what do you guys give for them? Anybody?
34.51%.
Okay, let's see. Yeah, so I get 0.3451. I like it. Question? Wow. We went for it. Okay. So now let me break down the parts of what we've done. So what is it that doesn't always have to be the same? I don't always have to ask for 1. I could have said exactly 2, exactly 3. I could have had more than 5 people, right? I could have had 1,800 people or something, right? So in general, I'm going to have n things. Thank God, n just always means the total number of things. In this case, we call it the total number of trials. So here's one trial, another trial, another trial. Right? I'm sorry. 1, 2, 3, 4, 5, this way. This is going to be something we're going to do in the calculator, because the calculator is basically built to count. My number of successes is x, because that's my variable. So for any group of people, you pick 12 dentists, how many of them prefer my bubblegum? That could be 0 to 12. So that's what's going to vary. So I'm going to call that x. X is the number of successes that I want. And then, of course, P and Q we've already talked about. Probability of success. Q, Jeff. Q. There you go, buddy. Probability of success and failure. Cool. I like it. So the formula is going to look like this so far. The formula for the probability of X successes is going to be that 5 is the number of, or let me see this, how long our list is. Times P to the X. Now, I'm going to let that make sense. Because what does X mean? The number of successes. So I want this many successes. Now here's the weird part of the formula, but it's an easy part. Why was that a 4? Because that's a 1, and how many total people did I have? 5. So if I got 1 here and I got 5 total, the rest, 5 minus 1, is 4. So in general, how many failures am I going to have? The total minus the successes. That's going to be what's left. So the formula makes it look harder than it really is. It's just the rest. Okay. So what we need to figure out still is this piece. And just to convince you that it's not always as easy as that is, what if I had 40 people? And I want to know the probability that exactly 5 are left-handed. Now, just start to think about this. And there's no way in hell we are going to make this list. But start to think, and that's not really that different of a problem, is it? From a math standpoint, it shouldn't be that different of a problem. I pick 40 instead of 5. I want exactly 5 left-handed instead of 1. Ooh. But from a human perspective, that list is going to be stupid insane. There's no freaking way. Because it could be the first 5, or it could be the last 5, or it could be the first 2, the middle 3, or it could be the second 2 and the 3 that are before the last one. Or it could be, oh my God, do you start? And I'm not even close. Do you understand what I'm saying? This was freaking easy. That's why I started with it, right? But just to make sure you understand why this formula exists, it's for situations that are just a little bit more. Okay, maybe. Okay. So what the hell, how do you figure this out? We're going to do this in the calculator. And the really cool thing about this is, I have a total number and I want to choose X of them. So how did we know there's only going to be one? Because I have 5 of them and I want to choose one of them to be left-handed so it'll match what I'm looking for, right? So I'll have a total number, and I want to choose this many of them to be successes. And there's actually a function in the calculator that'll tell you how long that list would be, how many ways there is to do that. And this is where if you work out with pizza toppings, you get the millions and millions of of different kind of pizzas available. And you get there's more ways to shuffle a deck of cards than there have been seconds in the existence of the universe. Hold that shit. Right? Look that shit up. Every time you shuffle a deck of cards, like more than 7 times to make sure you've really shuffled it, that the probability that that's never been shuffled exactly the same way is almost 100%. So you just do it and you're like, I just did something nobody in the universe has ever done before, right? All right, whatever. All right. So here's how you do it in the calculator. Let me put it over here so we can really see what's going on. No. I said no. No means no. Come on. All right. Oh.
What about the other one?
They did say no. All right, we'll use the other one. There you go. Okay. So I want to show you 2 things. I want to show you how to get the list up there. Can you turn the one off that says hi? Okay. And how to put the entire formula into the calculator. All right. So real quick, let's try to do that. Just try to do just the 40, choose 5. Do you guys see that? If I have 40 people, and I want probably exactly 5 left-handed people, then I want 40, choose 5. I'm going to choose 5 people from the 40 to be the left-handed people. And this tells me the number of ways to do that. I like it. And it goes here because that's where that's how many of these I'm going to have in my list. Okay. So let's see. Here's how you get to where it is. Ouch. 40. Then you hit the math button. if you're playing around with your calculator at all, I'm going to hit that math button, see what the hell it is. It's a lot of cool shit. It can turn stuff into fractions. But you want to go over to probability. If you have a newer one, there might be something else at the end, but go to the PRB, the probability. And now, do you see which one I'm talking about? The calculator uses a slightly different symbol, but which one am I talking about? Yeah, number 3. They use an R in there instead of an X. Right? So you don't want National Public Radio. You want number 3. So 40, choose. Is that the way your screen looks right now? How are we doing? Oh, yours is newer. So let's see. Let me put, what does the newer ones do? Oh, and you guys can't see any of this. That's too bad. All right. 40 math, probability, choose. Oh yeah, it just puts it like the little subscripts, right? Yeah, you get the C. Okay, I like it. You just don't have the NCR. You got just the C. I like it. The thing you got to be careful about, if yours looks like just has a C in the middle, when you put this next number in, you have to hit the over button so that it knows you're done putting in that number, right? Right now, I think you just hit enter. Hit enter, Jeff. There you go. All right, so that's how long the list would have been for that. All right, 658,008. That's how many things. So if you wanted to see where the 5 came from, what was this problem? There were 5 people, and I wanted to probably exactly one of them, right? So if you did 5, choose 1. 5, choose 1. You get 5. Because that's how many ways to choose one thing from 5 there is. I like it. Okay. So, okay, cool. So let's do a few problems with this and see how it really works. Well, that was quick. Let me see. I'll keep this up here, I think. That's why I wanted to put it over there. Oh, let's do that last one. So if I get 40 people, the probability to get exactly 5 left-handed. So I still have these two things are true. The mistake I see a lot of people make is they'll base the probability on how many people I pick. But if there's 11% of the population that's left-handed and I choose 40 people, can I suddenly change the number of people that are left-handed? No. These are the same. For any single problem, these do not change. Just because I take more people, I don't change the percentage of people that are left-handed. That's a little crazy. It's like, what? What? No, it doesn't happen. So this would be ncx p to the x q to the n minus x, which is a really horrible kind of... It makes it look a little bit harder than it really is. The idea is more like a story. I got 40 people. I want to choose 5 of them to be left-handed. So then how many of these do I want? 5. I love it. It's a little repetitive, but that's all right. Nothing wrong with that. A good story is repetitive. So I want 5 of these. So how many of these do I want?
5.
No?
35.
35. Because how many total people do I have? 40. So 5 of them are this. 35 of them must be this. In fact, what is 40 minus 5? 35. See, that's what the formula is trying to tell you. The rest. N minus x is the rest. The rest of the people. So what do these two always have to add to be? In this case, 40 in general, n. It's got to add to be the total number of things you've got. So how do I put this all in the calculator? I can put it all in at once. Because the choose number is going to be huge. And then the probability numbers, I don't know if you realize this, but if I did 0.89 to the 35th power, it's going to be stupid small. So if I put it all in at once, 40, math, choose, 5. Now if you're in the newer calculator, you got to hit the over arrow to come up, out of, down, below. Alright? That's like Stranger Things, but times 0.11 to the 5th, right? I want 5 of those. Times, I want the rest of 89 to the 35th power. Let's see if we can handle that. Sweet. I like it. So about almost an 18% chance that you would have, if I picked 40 people randomly, that there would be 5 of them left-handed. Yes, ma'am.
I just don't know. I'm not sure any calculus. Yeah, that makes sense. Somebody doing trying to.
Oh, let me see. Let me do it in the new calculator. Let me put it up. Let me
Does somebody have the overheat still underneath?
So see in the new, holy crap, that is really 40 choose 5 times 0.11 to the 5th over times 0.89 to the 35th. So let me do it again. 40, choose 5, hit the over arrow. It's telling you to hit the over arrow. Now when you do times 0.11 to the 5th, you've got to hit the over arrow to come out of the exponent. This is for the newer calculators. Over times 0.89 to the 35th. Bam. How are we doing? Good? Alright. Are we good? Y'all get that? Okay. If you're sitting there without a calculator, then obviously you're okay with that. So, okay. Okay, so let's try a couple more problems out just to really make sure we get the idea. And then I'm going to unleash you on another handout. And of course, before I'm going to do another handout, what do we have to figure out how to calculate? I told you, anytime I give you a new distribution, this is a probability distribution. I could figure out the probability of 0, 1, 2, 3, all the way up to 40. And that I put it x and p of x. It's a distribution of probabilities. So I have to have a way to figure out the mean and the standard deviation. I like it. And thank God, these are the formulas you guys, I don't care how little you like statistics or wherever you are with it, you're going to love these formulas. These are the best. I love it. I got the best formulas. The best formulas. So first, let's do another example, just straight up example of the probability. You're looking at the thanks, man. So say we pick 22 gross spot students. Students, we know the probability that a gross amount student takes stats is 0.72. What's the probability that we get exactly, what you got, Jeff? I don't know, man. I'll pick something. 16 that have to take stats. Right, let's do this one together. First off, a really, really good idea is, in general, to summarize what you know and give it the right variable names. So what does the formula require? It needs n, it needs x, it needs p, it needs q. So let's find this. What's n? 22. Total number I'm talking about. What's p? What's p? Nope. What's 16? 16 is x. X is the number of successes. So how many successes do I want? 16. What's p? 0.72 is probability of success. And I said that exactly 16 have to take stats, right? So I'm looking for people that take stats, so P is going to be the probability of that. So 0.72. So what's Q? 0.28. The rest. A lot better. And now you just plug and shove, really. And don't forget, though, you could see where the formula came from. We developed it. So now, of course, that was the hard part. Now the easy part, just throw the shit in the right place. So now it's going to be N, choose X, and then I want 0.72. I want 16 of those, good. And then 0.28, I want 6 of those, because that makes 22 total. I love this formula because you can the formula shows you the situation. I got 16 of these, and I got 6 of these, and that's how many ways I can do that. What do you guys get? Oh, man.
I just need to consider. I got 0.1875. Yeah. Yeah?
That's what I got. 0.1875, I like. The only time to completely doubt what you got is if it's bigger than 1 or negative or something insane, right? There's no way to have a good handle on how big to expect these probabilities to be. There's somewhere I can go, okay, they're probably getting a certain kind of card out of a deck of cards should be kind of low. But here's I don't have a clue, huh? You know? But would you expect more or less? Would you expect more than half or less than half to be have to take stats?
Less.
What's the probability that somebody has to take stats? 72. So can we figure out exactly how many students I would expect to see out of 16? Out of 22.
More than 11.
Say again?
Would it be more than 11? Because
Totally more than 11. In fact, like I just said, we can figure out exactly what it is. What percentage of all gross plus students have to take stats? 72%. So what percentage of any group of randomly selected gross plus students? 72%. So what is 72% of 22? $18.92. And that's why I picked 16, because I knew it was close to this.
Wait, what? 22 times 0.72? It's 15.84.
15.84, it's better. Something close to 16. 15.84. I'm not even trying to do the math right now. You guys all have calculators, you can help me.
Yeah, that's exactly.
Maybe if you crowdsource and get the most of it. But what did I just get? What did I call that? What did I use the phrase? The expected number of people. Expected value is also a name for the expected value. It's the name for the what? The expected value. It's the name for the what? Do you remember? What was the formula for it? XP of X. It was this here, right? EXP. Expected value is another name for the mean. Yes. The mean is the expected value. If I had to guess, if it took like 7 random gross plus students, I had to guess their average age, I would guess the average age of all gross plus students. That's the expected value of any group of gross plus students. So what's the expected value of the number of students out of 22? 15.84. That's the mean. That's the average. So I took a bunch of 22 gross plus students, randomly selected, and then averaged the number that have to take stats, I would get 15.84. That's what that means. So that's the formula. You're gonna love that shit. What is the formula then? What do we do? What's 22? What variable is it? N. And what's 0.72? P. There's the formula for the mean. Now let me say it like this. Oh, I used to pick on Shaquille O'Neal, but now he's because he was on the Lakers. Of course, the Lakers suck so bad. Celtics fan right here, big time. And Celtics suck real bad too. So not so bad this time. I like it. The recoming of Isaiah Thomas really helped us out. So Lakers suck so bad. So if Shaquille O'Neal made 30% of his free throws, if I want to be nice, and he takes 20 free throws, how many would you expect him to make? How would you figure it out? Tell me the number.
30%.
If he makes 30% of his free throws and he takes 20, how many would you expect him to make? How would you calculate that?
20 times 0.33.
What?
Yeah, 20 times.
Yeah,
0.3.
0.30 times 20. Exactly. The percentage times the number. NP. Right? And why was that a binomial? Because either he makes it or he don't. Right? Now, I'm not going to go in depth with the standard deviation formula. It's a little bit more difficult to prove. You have to use something called math induction to prove it, but let's just live off of the work of others and realize the standard deviation in this case is the square root of NPQ. So the average for this situation, out of 22 students, I expect about 15.84. Now you see why I picked 16. Because in my head I did it real quick and I figured it was somewhere around 16. What's the standard deviation for this? It's going to be like a little over 2, 2.017. Was it?
2.106.
Oh, so close. That sounds about right. That's what I expected. What's up?
Are you going to ask to find the standard deviation?
Oh,
Okay, yeah, just...
Sorry.
And it's safe to
Yes.
use that little.
Totally. Yeah. I love the question because I can hear in your voice you're like, that can't be it. Right? Because what have we done for standard deviations? Sum of x squared p of x, and then plug that sum of x minus the mean squared, and then divide that, and then square. Oh my God! You have to make this huge table. That's all it takes for a because I know it's binomial, which tells me actually a lot of information by itself, which is why the formula is so simple. I like it. So now we can start to think about how to answer a question like this. Let me first do one thing. I think I've said this at some point before. When do things start to get unusual is when you get how far away from the mean. I think I've said this at least once maybe, but when you get 2 standard deviations away from the mean or further. Right, so to find the max and min usual values, well, you take the mean plus or minus 2 standard deviations. So if you start at the mean, you go up and down 2 steps, you expect the value to be in there. So before today, if I said, if you flip a coin 100 times, would it be weird to get 60 heads? Would that be like really weird? No. Would it be really weird to get 80 heads?
Yes.
Okay, yes, right? So somewhere in there, where exactly is the line that I can draw? That's the question I sometimes get from people. And I'm like, well, even 50, now realize 50 heads, that would still also freak me out a little bit because I got exactly 50 heads, but that should be the most likely thing to happen, right? But our brain says, yeah, but that's one thing, so something else will probably happen. So when that happens, we go, oh, neat. Plus, you kind of evaluate your life if you're sitting there flipping a coin 100 times. But, that's a whole other thing. So if I was going to flip a coin, obviously, and I'm going to do it 100 times, and I'm looking for heads, it doesn't really matter there, because what would P and Q be for flipping a coin, a nice, fair coin?
0.5.
0.5 and 0.5. So this is a way to check to see if a coin is weighted or not, is to see if it gives unusual results. But to see if it gives unusual results, we have to have a definition of unusual. Hey, we do. Later in the course, this number might change. So, for example, I know I'm going off on a few tangents, but I can't stop. If I work at a nuclear power plant, am I going to wait till that needle gets in the red to get off my ass and go look at something? No, I'm probably going to. The minute it starts to go towards the yellow, the minute it starts to move towards the yellow, I'm going to freaking go take a look, right? I'm not going to Homer Simpson the thing. No, Simpsons. Yeah, they've been around for a long time. Holy shit.
Plutonium? Is that what?
Huh?
Plutonium. What was the count? Isn't it like plutonium? Or what was it called? It was the Simpsons.
Simpsons. Well, it's also just nuclear power plants in general. Yeah. But this number might change depending on how bad it is to not consider something unusual. So for a power plant, I might make it even 1. Like if the needle goes 1 standard deviation away from where the average, I'm going to get up and go take a look. But in general, we consider it to be 2 steps away. That's when we think about things being unusual. Anything outside of it. So if your height is 2 standard deviations above or below the average height, you have an unusual height. Doesn't mean you are unusual. It just means that we don't see somebody with that height often. Okay, I like it. So, what's the mean for this going to be? Obviously, it's going to be. Don't even need a formula. Flip a coin 100 times. What's the average number of heads? 50. 100 times 0.5? 50. 50, yeah. And then the standard deviation is the one that you can't just rattle off to me, but you can do the work. Five, yes. So 100 times 0.5 times 0.5. Half of 100 is 50, half of 50 is 25. The square root of 25 is 5. Don't even need a calculator. So what's the least and the most number of heads I expect to get? The minimum would be minus 2. So 50 minus 2 of these is 40. So that's the minimum number I expect. And the maximum number I expect would be 50 plus 2 of these. 60. That's why I started with 60. And you guys said, oh, it's right on the border. I would think that's a little... See, that matches up with the official definition for now. So if I flipped a coin and I got 70 heads... That is actually evidence that something is unusual. Now, is that proof that something is unusual? No, but it's evidence. There's a difference there, right? There's evidence, and then there's proof. Right? Okay. Do you guys really? Yes.
An example. I was just thinking of like in the NFL, like how much a ball weighs. Is that?
Oh, you think about Deflategate?
Yeah.
When in doubt, just assume the Patriots cheated. Number 1. I'm sorry. If you like the Patriots and the Lakers, we do not see eye to eye on
I
this
like the
one.
picture. The Lakers are the sole team. I do not.
But yes, they used statistics to figure out that it was an unusual inflation, even for the weather.
But it wasn't exact proof, right?
It wasn't total proof that somebody did it on purpose, but it was evidence, right? Yes. So we're collecting evidence as we do this. So statistical analysis, why can it never prove anything perfectly? Because it's all probabilities. It's real life. People wish that math could just go, yes, it is definitely him. Oh, put him away. No, but that's not the reality, right? You've seen movies that are based on this idea and it's horrible because it doesn't work. People try to make technology do more than it wants to or than it can, and math is the same thing. Okay. So let me shut up finally. Let me give you guys this paper here. Are you still going?